In this video, we will do Ehrenfest theorem or time evolution of expectation value. Let's consider we have a state phi that depends on time. Further, we will consider state phi is normalized, so scalar product of phi is equal to 1. Now consider expectation value of linear operator which we defined A is expectation value of operator A is equal to phi A phi. This is question number 1. Now take time derivative of equation 1. So d over dt, expectation value of A is equal to d over dt phi A phi, which is equal to partial over partial t phi A phi plus phi partial A over partial t phi plus phi A partial phi over partial t. Now, when Hamiltonian acts on any state which is phi, it gives us iota h cut partial phi over partial t, and partial phi over partial t is equal to minus iota h phi over h cut. This is equation A, this is equation B. Now take dagger of equation B. We now iota change into minus iota and cut change into bra, and we further know that h dagger is equal to h. So after taking the dagger of equation which is adjoint, equation B become partial over partial t phi iota phi h over h cut, which is equation C. So put equation C in first term and equation B in third term. So time derivative of expectation value of A become iota phi h A phi over h cut plus, and this term is equal to expectation value of time derivative partial A over partial t minus, and this term is equal to phi A h phi iota over h cut. Now we combine first term and third term, which is equal to iota over h cut phi h a minus a h phi plus expectation value of partial a over partial t, and we now commutator of h a is equal to h a minus a h. So this term is equal to the commutator of h and a. So time derivative of expectation value of a is equal to iota over h cut phi commutator of h and a phi plus expectation value of partial a over partial t, and this term is equal to expectation value of commutator h and a. So this is equal to iota over h cut expectation value of commutator h and a plus expectation value of partial a over partial t, where h is Hamiltonian and a is any linear operator. We have find the result. Time derivative of expectation value of a is equal to iota over h cut expectation value of commutator h and a plus expectation value of partial a over partial t. Further, if we consider case 1, if a does not depend on time, explicitity, then partial a over partial t is equal to 0. So time derivative of expectation value of a is equal to iota over h cut expectation value of commutator h and a. Further, we consider a and h are commute, so commutator is equal to 0. So time derivative of expectation value of a is equal to 0 and expectation value of a is equal to constants. Now we consider operator a is momentum. So time derivative of expectation value of momentum is equal to iota over h cut expectation value of h and p plus expectation value of partial p over partial t. Since momentum does not depend on time, so partial p over partial t is equal to 0, and Hamiltonian is equal to p square over 2m plus v of x, where v of x is the potential energy and this term is the kinetic energy, and this is potential energy. So commutator of h and p is equal to commutator of p square over 2m plus v of x and p, which is equal to p commutator of p square over 2m and p plus commutator of v of x and p, and commutator of this term is equal to 0. So commutator of h and p is equal to commutator of v of x and p. Further, which is equation, now we consider this is equation A and this is equation B. Further, commutator of v of x and p depend on some function which is f. So this is equal to v of x p minus p v of x f, and momentum is equal to minus iota h cut d over dx. So this is equal to v minus iota h cut partial over d over dx f minus iota h cut d over dx vf. This is equal to minus iota h cut v df over dx plus iota h cut f dv over dx plus iota h cut v df over dx, and this term are cancelled out. So commutator of v of x and p is equal to iota h cut dv over dx, and dv over dx is equal to gradient of v. So equation A become time derivative of expectation value of momentum is equal to iota over h cut expectation value of, and commutator of h and p is equal to commutator of v and p, which is equal to iota h cut gradient of v. So it is equal to iota h cut gradient of v, and this term is equal to 0. So iota square is equal to minus 1. So this is equal to minus expectation value of gradient of v. Now consider linear operator A is equal to x, which is position in one dimension. So time derivative of expectation value of x is equal to iota over h cut expectation value of commutator h and x plus expectation value of partial x over partial t, and position does not depend on x. So partial x over partial t is equal to 0, and Hamiltonian is equal to kinetic energy plus potential energy. So this is equation C. So commutator of h and x is equal to commutator of p square over 2m plus v of x and x is again equal to p square over 2m and x commutator plus commutator of v of x and x. Since potential energy depends on x, so commutator of v of x and x is equal to 0. And we know commutator of x and p is equal to iota h cut. Commutator of x and p square is equal to 2 iota h cut p. And commutator of p square x is equal to minus 2 iota h cut p. So commutator of h and x is equal to minus 2 iota h cut p over 2m, which is equal to minus iota h cut p over m. So equation C becomes time derivative of expectation value of x is equal to iota over h cut expectation value of minus iota h cut p over m, which is equal to expectation value of p over m. So we conclude time derivative of expectation value of x is equal to expectation value of p over m, and time derivative of expectation value of momentum is equal to minus expectation value of gradient of v.